Students, for today's lecture, we will focus on an important concept called polymorphism and allotropy. So for a lot of materials, you can have more than one crystal structure. And this phenomenon is called polymorphism. And in elemental materials, this is also called allotropy. Okay? A very good example is the polymorphism and allotropy of carbon material. And in today's lecture, we are going to use carbon as an example for discussion. So the most precious form or the crystal structure of carbon is actually this diamond. And diamond is very precious and it's a gem, and it has essentially a so-called diamond cubic structure where essentially you will have two interpenetrating FCC structure for diamond. And the two FCC structures, they are relatively displaced from each other by this 1/4 or a quarter of body diagonal. And this is your diamond cubic structure. A second form of carbon in nature is called graphite. And graphite appears completely different from diamond. And graphite has its unique structure, completely different structure than diamond's cubic structure, where you will have a hexagonal symmetry typed carbon items in the plane, and then a lot of such carbon planes will be stacked together and forming this graphite. So that's a graphite structure, and it's also pure carbon. And then you may have this fullerene structure, where it's just like a football. So you have carbon items on the surface of this football. Essentially, the difference in the crystal structure, they will have their origin in a different bonding state in the crystals. And for carbon items, you know that there are 6 second shell electrons, right? So you have 6 second shell electrons, 2 2s electrons, and 2 2p shell electrons. And depending on the bonding state, you may end up with different crystal structures. And 2 types of bonding formation can happen. One is the so-called sp2 hybridization, and the other one is this sp3 hybridization. So in the sp2 hybridization, essentially you have the 2s orbital mixed with 2 of the 3 available pi or p orbitals, forming a total of 3 sp2 orbitals with 1 remaining 2p orbital. So essentially you will have 3 hybridized orbitals in the plane, and then you will have 1 unpaired or unhybridized p orbital in the z direction. So that's called sp2 hybridization. And this gives rise to your graphite structure, right? So in this graphite structure, in the plane of a graphite plane, and you will have carbon items connected with each other having these sp2 hybridized chemical bonds, okay? And in between the planes, you will have relatively weak van der Waals interactions because of this unpaired pi orbital. Okay? So that gives rise to your graphite structure. And there's also the origin or the foundation for your fullerene crystal structure. And then we move on to your sp3 hybridization, where your 2s orbitals is mixed with all the 3 2p orbitals, forming 4 sp3 orbitals. So essentially you have 4 electron orbitals that are equivalent to each other, which will give rise to a tetragonal symmetry. And this is exactly the case for your diamond cubic structure or diamond structure, where you have this tetragonal symmetry for your carbon items, and all the chemical interaction or chemical bonding between your carbon items is this sp3 hybridized chemical interactions. So for today's lecture, you know that the different bonding state in carbon gives rise to your different crystal structures and gives rise to your polymorphism and your allotropy. This is today's lecture. Thank you very much.